So today we will talk about what I call full conformal field theory. And I will need take some time to explain what I mean by that, and then give you a construction of correlators for the case of rational conformal field theory. And let me start with recalling a few things we said yesterday, so last week. I said that what I call chiral CFD is characterized by some vertex operator alpha V, some category of V modules, and then systems of conformal blocks, which we have introduced in the first place as vector spaces of solutions to certain differential equations, which implement the symmetries of a vertex algebra V on roughly a tensor product of vertex operator algebra representations, where the action on which is given by a sum of actions locally on each of them, where locally we interpret the formal variable that we have in the vertex algebra as a local holomorphic coordinate. And I have also mentioned that in the first place is the vector spaces, then we have considered them as bundles over some modular spaces, first for fixed genus, and then mentioned that we have sewing relations by which we actually get bundles over a modular space of stable curves. And then I also mentioned that we have another way of using the term by, in the first place, just looking at these spaces as finite dimensional vector spaces, finite dimensional in situations where, for example, the vertex algebra is rational, but also a bit more general could be allowed. And we have these vector spaces, and they are endowed with these sewing relations between the vector space, the vector space associated to different surfaces, and they carry representations of the mapping class groups. And mapping class group of, well, we have first maybe started with the type of surface that we are looking at. We are interested in conformal field theory, so we have a conformal structure on two manifold sigma, but we also assume in this situation that we have chosen globally an orientation, and then we actually deal with complex curves, and this is what we need for these modular spaces here. And let me mention this is relevant, for example, in algebraic geometry, when for a particular subclass of vertex operator algebras, one derives what is called the Berlinde formula. And let me give it in full generality, which is not the way it's typically written in conformal field theory. One only considers a special case, but it's the way which arises naturally in this algebraic geometry context, for example. So we have these vector spaces which depend on the genus G of the curve and labels lambda describing the simple V modules which we the tensor product of which we consider, and then this can be written as sum of mu and lambda. So we are now in the case that C, the category of modules that we consider is a modular fusion category. And then we get the formula that this is a sum over a product over all I, and then we have S lambda I mu divided by S0 mu, and this multiplied with 1 over S0 and mu to the power 2g minus g. And so in the case of the sphere, which one often starts with, this factor is not there, and then often one also looks at the situation that m, the number of tensor factors, is equal to 3. And the matrix S here, remember, comes from the modular transformations of current.
Is it 2g minus 2?
Thank you. Now, in contrast, and I should also mention, there are situations in condensed matter physics where one deals with systems which generally one can call chiral electron systems. And this is, for example, what you deal with in fractional quantum Hall effect situations. And now in contrast, and also that we have to some extent already said in section 1, we want often, and in particular in applications that I am interested in, we need correlators, which are correlators in the ordinary quantum field theoretic sense. So they should be functions, single-valued functions of the positions Bi of these where we have our fields which carry those representations of the vertex algebra, and we could also say function of these local coordinates we choose there, and of the moduli of the surface sigma. And let me to be precise, not right sigma here. The point is that it is not necessarily well, we will not deal with a complex curve, but just with a conformal manifold, and we'll say more about this. But also, what we already had before is that they depend functorially on the lambda i's, but also they may depend on other data of the surface. And so far, we do not have any other data, but I will tell you what kind of data there can be. And we have seen, well, in general, the sections of this vector bundles are the horizontal sections with respect to this Knight homological equations are not have a non-trivial topology, and so we cannot use this chiral theory directly, but there's a good reason that we first looked at it, and I will come to that. But let me first say what we want to look at, our surface will from now on be what I call the world sheet. Terminology borrowed from James theory, and I will denote it by S. And from this surface, we will get a certain complex curve sigma, which is determined completely by S, but which as a surface is not necessarily the same. I will often suppress the index S here, and unfortunately sometimes might confuse in the notation S and sigma. I hope that I will not do that, but I cannot ensure that this will not happen. So what do we mean by this worldsheet? So first of all, it's a conformal manifold of dimension 2. So it has a conformal structure. But for what we will be doing, actually conformal structure will not be essential. I mean, it will not appear explicitly. Now, possibly S might have a non-empty boundary. That's not possible for sigma, and also possibly S might not be oriented. In particular, it might be non-orientable, and even if it is orientable, we might choose not to, might decide not to consider a particular orientation on it. And I already mentioned worldsheet. The terminology comes from string theory. The reason, or one major reason to look at non-orientable worldsheets also comes from string theory, so-called type 1 string theory. But there are also applications in condensed matter physics. So, for example, one has actually been able to create something, some two-dimensional surface in a three-dimensional system, which is the topology of the Memphis. And then I mentioned the conformal structure is an equivalence class of metrics. This matrix should have Euclidean signature, and is in particular because the surface will be allowed an arbitrary number of handles, and we require it to be compact. Partly for technical reasons, but there are also in applications you can actually explain why this is a good idea. And now on a compact surface, metric with Minkowskian signature only exists if it has genus 1. So we want to allow for arbitrary genus. And now we want to define a kind of conformal field theory where we deal with a surface of this type, and where we get a correlator satisfying these properties. And this I will then call, for the lack of a better name, full conformal field theory. Sometimes it's also called local conformal field theory. Or if you want to be sure that you are not misunderstood, you can say full local conformal field theory. And I would like to have a more specific or more explanatory term for it, but we couldn't come up with anything. And indeed, collaborators mine and me invented this term in a sense, because we saw the need for having a term for it, because in the physics literature there was quite often confusion between chiral and full conformal field theory, and people were not always aware of what they were actually doing. But nowadays the term seems to be largely accepted. So let's see how we can now formulate something we want a conformal field theory in such a situation. And the basic idea or prescription is that we relate it to chiral CFT. And we know a lot about chiral CFT, and then we can use that knowledge. And what does this mean? First of all, geometrically, and I have to say much more about this later, but for now, this simply means that we on S, they have a conformal structure. And then we take a choice of local orientation. And then we will get from this a suitable complex curve sigma. In the simplest case where I can do this locally, then I will just get directly because there are two choices. So we will deal with a double cover of S, and in the simplest case, this will just be disconnected sum of S or the underlying just surface. There will be other. So let's call it of like sigma S. This will in the simplest case just be a disconnected sum of two copies of the same curve, but with two different choices of orientations. And representation theoretically, this means that the fields that we will have to consider do not just carry one representation of the underlying vertex algebra, but actually two, and in principle of two different vertex algebras. So these, again, terminology from physics or from string theory, one combines left and right movers, and this terminology comes from the particular theory of a free boson, and where one has field equations which are two-dimensional solutions, have two-dimensional waves, one space and one time dimensional, so space waves, and they can move to the right or to the left, or also chiral, two chiral halves, something like that. Some people call them also chiral and anti-chiral, or holomorphic and anti-holomorphic. There are many terms in the literature for that. And this idea or this prescription has also sometimes been called holomorphic factorization, a term I think coined by Witten. And this means for us the following, that a field carries a representation of some vertex algebra V, which I now call VL, L for left, and also another one for right, and I have the take a tensor product of those. So what we deal with is a category of modules over such a tensor product, and this is equivalent to considering if we considering modules over L, and then the linear product, assuming our situation is such that it exists, VR mod. And I should say right away, in situations where the linear product doesn't exist, there are generalizations of it where hopefully one can use it. If one does not know anything about this representation categorically, then one cannot be sure that such an idea will work at all. So and there are definitely conformal field theories, Cardiac conformal field theory, which are outside this framework, in which one knows that such things as I will describe them will work. But I had the impression that a general idea in physics, at least, is that anything you want to call conformal field theory will in some way still fit into this picture. And we will restrict also to the case that actually, if we call the modules over the first vertex algebra C, then we consider the situation that the other one also gives a C, except I write C ref. That stands for taking the inverse or reverse of the braiding, and also the inverse of the twist on the category. There are situations in conformal field theory where this is not true. They are called heterotic theories, and there is a possible extension of the framework to those, but it makes things more complicated, and conceptually it's not so interesting anything. Importantly here now, that means that we deal with, in this, we take this expression, we deal with a category of the form the linear product of the red, and know that this is braided equivalent. I think I mentioned we have talked about this before, to the differential center of C, and this is a very significant aspect, but I will not have time to say much about it. I will occasionally use what does this mean in more detail? First of all, on my worksheet S, I can have bulk fill or bulk fill insertions. Those I will denote by phi, and they will have two labels in. I'm considering in generality. Not write this now. In principle, I have here just two labels. Let's call them X and X prime, where these correspond to V modules. And also for given such labels, there might be not everything. We always have a C-linear structure here. So there will be a whole space of these, and this space for given X and X prime might not be one-dimensional, but have some dimension, and then we add a label alpha here, so for some choice of basis in that space. And I will often refer to this as a multiplicity label. And in the case that C is a modular fusion category, then we can take X to be Y lambda and X prime to be Y lambda prime, and then we will do this for lambda lambda prime with this set called capital lambda. Now, geometrically, so this is the representation theoretic aspect. We have some point on our worksheet, which is talking about the insertion point. And the local coordinate, local holomorphic coordinate around P. And this corresponds in the way we have done in chiral conformal field theory to the formal parameter Z in vertex algebra. And when we need to do things in a sufficiently precise form to include these or some aspects of these coordinates, we will actually think of this in two possible ways. We have this point P, where we can cut out a small disk from our worksheet S and use the local coordinate to get a parametrization of this circle. Another possibility, which I will use when I come to the ribbon graphs, is that I take what is called a term of arcs. So I take a family of arcs which are of arbitrarily small lengths, which goes through P and have a certain direction. But that's not all. There can be also boundaries. Now I have to be careful here. I have already, if I use this picture, I have already introduced boundaries. But this, if I need a term for it, I will also call it gluing boundary, because it turns out this is of the same type as the boundary circles that we have when we glue surfaces in the sewing process of curves. Whereas there are in general also components, connected components of the boundary, which one calls physical boundaries. Some people call it end of the world boundary, and there are many other names for it. They are just not of this type. So first of all, they are not parameterized, but then they also carry some label, which I will denote by B, and I will have to tell what the values we can take. But for the moment, this is just a label. No, not B. B sounds like boundary, but I will use the label. And we will see a bit later why. So once we have, but then that's only part of the story still, because once we have such a boundary condition, we can also have boundary fields. So we have such a boundary, some segment of this boundary which of this type. Then we can say we choose a point P on this boundary, and then to the left and right of P, actually let it be oriented. We will in general have different boundary conditions M and M prime, and then we can say this corresponds, just like here we have a bulk field. Now we have a boundary field, which I denote by capital psi. We'll have labels M and prime. And in addition, I'll put them here. And it turns out that they should again carry some representation of underlying vertex algebras. And in this case, when bulk field is something in a two-dimensional part, this is in a one-dimensional stratum, so accordingly it carries only a single representation. And I wrote lambda here, this is again in the rational case, in generality, with some representation X, a module of the vertex algebra. And here, a word of warning: if you should read some literature, which by physicists or physics inspired, very often they say on the boundary, or you will see something either explicitly or implicitly, that on the boundary you have a chiral theory. This is simply not true. What is true is that just one copy of your vertex algebra is relevant. But the boundary has, or each segment of the boundary has such an extra label that we didn't have for our curves sigma, and also on those curves we don't have any insertions of fields. Apart from these boundaries, we can also have something one could call inner boundaries. Still not done. This is a problem, though. Do we have an? Oh.
This is what?
You have to find something that won't break. If we can also have an inner boundary, or let's call it a domain wall. Sometimes we also have a defect. A wall, it's just a line. What we call a defect or defect line. So if we are in the bulk of in the interior of our worksheet, we can have some line which has to be closed or end maybe on the boundary. We can be oriented and we give it some label, which we call a defect type. And this I denote by B. So I have here. And then I can also have defect fields, namely insertions at some point P on such a defect line, and those I will denote by capital theta. They have, again, just like ordinary bulk fields in the interior, two private labels, but now they will also depend on two of these defect labels, and again, I haven't determined what they are conceptually. That we will have to explain. There is one type of defect which we will always allow. It's called the invisible defect. So it's just like there is none. But if you have an insertion on an invisible defect, then a defect field changing the invisible type of defect to the invisible type, then this is just an ordered bulk field. And so bulk fields are just very special cases of defect fields. Also, defect fields can start or end at such insertions. In condensed matter physics, one has a special name for them. Something I will not write down is we can also allow in principle for defect junctions. But I will not do this for brevity here. One can think of defect junctions again by cutting out a small disk there and then associating a generalized defect field to that circuit. And in principle, you can have several defect fields ending at the same point on the boundary. So you have generalized boundary fields and boundary defect fields. So there's a lot more you can do, but you can reduce it always to this situation. Just having these things. But this is considerably more complicated than what we have considered so far. And now I say full conformal field theory on the worldsheet. And this is a spirit of some approach to general quantum field theory is the same as a consistent full conformal base on the chiral theory with underlying category. D is a consistent system of correlators in the rough sense that I had described on all possible worldsheets. So arbitrary genus, arbitrary types of field insertions, arbitrary defects, arbitrary boundary conditions, and so on. And as we will see later, so this is, we can think of this as an assignment to each such worldsheet S of something we will call the correlator based on the chiral theory C for S. And this we will determine as an element of the space of chiral blocks on some complex curve, and this will be the curve that I denote by sigma S. And I still have to tell you what that is. And consistent here, I don't write it down, is first of all, it should be invariant under the relevant mapping class group. What that is, I will tell you a bit later. And it should be compatible with sewing. That means if I have two surfaces which I can sew together, then the choice for correlators that I have for the original two surfaces, if I use the sewing maps that I have from the chiral theory, then those specific elements in the two spaces of conformal blocks will be mapped to the specific element given in this system. And it's by no means clear that such a thing, a solution to this exists, but it turns out, and I will give some more details about this result later, but already want to have it once here. As a classification, that we assume that C is a modular fusion category, and there are some further restrictions which I do not want to mention now. If I have time, I will do it later. Then there is a bijection of such consistent systems of correlators, and Morita classes of a certain type of Frobenius algebras. In C, and this, in the way I formulate it now, is if we do not consider defects, but the statement can be generalized to, and in a way we will also see later to what happens when we include defects, and also in this case, if you just have this description, then you assume S to be oriented, but again, it can be generalized to the not oriented case. And let me briefly tell you what the relation of these quantities I described these Frobenius algebras is, and that's the second part, a construction where these descriptions will arise very naturally. So let's call this algebra A. It turns out that, well, what is relevant in this projection are Morita classes of algebras. But if I want to say something concretely about a role, then I have to change to choose some representative, which I again call A. And then we have that the boundary condition M will be an object in the category of A modules. And all of this is for the rational case. Then the space of these boundary fields with chiral labels lambda and boundary labels m prime will be or correspond to space of morphisms in the category of A modules of I wrote this for general X even X tensor m and prime where M and X, where I regard this object in C here as an A module by acting with A on the first factor.
X is an option of C, is that correct?
Can you say again?
What is S? X an option of C or
what is
X?
X. That's just like I did it before. So in our case of rational conformal field theory, without loss of generality, we can take it to be a simple object.
A module means left-hand module or right-hand module or right module?
If I say A mod, I introduced it before, I mean left modules. I could also choose right modules, but not bimodules. Bimodules will appear in the second. Maybe the defect types. B are objects in the category of A bimodules. Or more generally, if I have such a defect, then I can allow for the situation that on one side of it I have I deal with such an algebra A, and on the other side a different one, A prime. So here A would, with this orientation, act from the left and A prime from the right. And analogously, if I look at the vector space of defect fields with chiral labels lambda x and x prime, and defect labels b and b prime, then this will correspond to the bimodule morphisms of. Now it's a bit more complicated. What I need now is to make this object in C here into a bimodule, A prime bimodule, and I do this in the following way, indicated by this plus and minus here, that graphically I have say B here, X and X prime here. Then I say that the left action of A on this is given by using the braiding, and the right action is given A prime. is given by using the inverse gravity. And this turns out to be the right thing to do. And then I haven't talked about bulk fields, but for bulk fields, just A and A prime will be trivial, namely the object monoidal unit 1 with trivial morphisms. And then, sorry, it will be the trivial defect, namely x equal to A and x prime equal to A prime. No, here A, B equal to A and B prime equal to A prime. Then we will have bulk fields. And that's, it's time to stop, but let me just start with one line. Yeah, what we will do. And I will do this mainly by just drawing a big picture. Something that has been called the EFT construction of correlators for consistent system of correlators for rational conformal field theory. This will, I will give a prescription. It's a bit lengthy, and I will not describe all details, but the details are completely worked out. Let's have a break. This TFT construction, there are two basic parts or steps. The first part, what I will treat this as a second, is that we associate to the worksheet with all this additional structure a certain written graph in a three-manifold, which I call MS. So M stands for manifold, but I implicitly specify a written graph. If I need the name for that, I might call it gamma, but typically I will not. And then the second step is we apply reciprocally derived type three-dimensional topological field theory. So what is the topological field theory for the purposes here? It's a functor RT from the category of 3,2-dimensional oriented cobordism. So objects are two manifolds oriented and maybe some a little bit of more structure, which I will not talk about, and morphisms between two. I draw it one-dimensionally, and in the 2,1 case, we would have as objects one-dimensional manifolds, and the morphism is a cobordism. So that means one dimension higher manifold, which has an incoming boundary given by the first and manifold and outgoing by the other. You consider a functor from this cobordism category to the category of vector spaces completely over C. It would be symmetric monoidal, where on vector spaces I have the ordinary symmetric monoidal structure, tensor product over C, and then flipping elements in the tensor product. And here the tensor product is disjoint union, and the symmetric monoidal structures with exchange symmetric structures. This tensor product is symmetric. And so what does this do? I want to write it down a bit more concretely. I take a two-manifold, I associate it to a vector space, and I take a cobordism between two manifolds and associate it to a linear map between the corresponding vector spaces. And this should be compatible with the symmetric monoidal structure. So in particular, if I take here the empty set as a two-manifold, this will go to the monoidal unit in vector spaces C, and if I take disjoint union, this will go to RT of sigma lambda product over C with sigma prime. And also that's not only true for objects, but correspondingly also for morphisms. I don't write that down. And also it should, in addition, it should be compatible with floating. This is some kind of an extra condition in the description I have here, but one can actually do things more conceptually, and then this is included. An important result now by Rashidin Tourayef and others is that if I have a modular fusion category C, then gives such a function. And let me just again, for brevity, describe this only in words, or mainly in words. Let's look at the situation that my 3-manifold is M3. Is the 3 sphere S3. I allow actually, so one should say a little bit more here. I allow for embedded ribbon graphs into in that 3-manifold. If my 3-manifold is S3, then up to normalization, I take that ribbon graph in the 3-manifold, project it non-degenerately to a plane, interpret the resulting picture as a string diagram for the category C. So the ribbon graphs will have segments which are labeled by objects of C and coupons which are labeled by morphisms. Then this is in particular closed, so that means it's a morphism from the empty set to the empty set. So I have to get a linear map from the complex numbers to the complex numbers, meaning a complex number, and that complex number is precisely the one that I get by identifying the endomorphisms of the monoidal unit, which, remember, in string diagrams is invisible if I identify them with the complex numbers. If the manifold is more complicated, but still has empty boundary, then one uses surgery to relate it to S3. So concretely, one takes out one neighborhood of a closed ribbon, which is essentially a full cylinder, applies a modular mapping class group transformation to it, and then in this way can get, if one does it, every such manifold can be brought to an S3, and then one has to keep track of what one has been doing in terms of ribbon graphs, and then afterwards using the prescription here. And then if the boundary is not 0, then on the boundary, that's indicated by, now we have really 2 manifolds. So on the 2 manifold, I can have insertions, mark points, and again, just like I mentioned before, I think of terms of arcs associated with them, and at those, then ribbons can start or end. Inside there is some ribbon graph. And in this case, what I get is a linear map from the space, the state space. These vector spaces are called state spaces. The state space associated to here, I have labels lambda, lambda, lambda 1, lambda 2, and so on. Will just be the space of morphisms in C from lambda 1 tensor lambda 2 and so on to 1, or the other way around. It doesn't matter because we are semi-simple. And then instead of dealing with string, again, you have to bring this to some standard form so that you can use string diagrams now, say for S2 cross an interval or something like that, for which one easily gets prescriptions, and in the end, everything is boiled down to evaluating morphisms in C. And this we now use to say that, remember in the first step, which I have not shown yet, we obtain or construct some three-manifold with embedded ribbon graph, which is determined by the worldsheet, and we think of this now not as a three-manifold just, but as a cobordism from the empty set to the boundary. So if we now take the Reshetikhin-Torayev functor, then we will get a linear map from the vector space associated to the complex to the empty set, which has the complex numbers, to the state space for the boundary, and this state space we interpret as the conformal block space. As a space of conformal blocks via, I mentioned last time, you have this concept of modular functor, which is roughly the two-dimensional part of a three-dimensional topological field theory, and there is a general statement probably proven in the last class of cases that topological modular functor, where I deal with the state spaces of a topological field theory, is equivalent to a complex modular functor, where I deal with actual spaces of conformal blocks coming from a vertex algebra. So I think of my state spaces, of my spaces of blocks, from now on always in this way, just these vector spaces, which I get as state spaces of topological field theory. And so this is a map of this type, and now I apply this map to the number 1 in the complex numbers, and by this I will get an element, a vector in this space, and this I will define as the correlator that I associate for the chiral theory labeled by C, or determined by C, that I associate to my worldsheet S. And so in just in one sentence, step B means I take the result of step A, which I have here. I apply Reshetikhin-Torayev. I get an element in a certain vector space, and that I take to be my conformal block. And now I have to tell you what this first part is. This was actually 35 and then 36. And then 37, I describe the construction or main steps in the construction of MS. And for that, I have to start with the following. I take sigma S. So this is, by this I mean the surface let me just call it sigma. The surface underlying S. So forget if there are any defect lines, I just ignore them. But boundary I have to include, and then we form what I call sigma hat, which is called the oriented double. There's a general description, which for brevity I will not. No, let me say it. You take what is called the orientation bundle of sigma. So locally, you just choose two sheets corresponding to the two possible orientations, and you divide out an equivalence relation, which says that for any point P with orientation OR, I take the same as P with the opposite orientation, provided P is in the boundary of sigma. For example, if d sigma, if sigma doesn't have a boundary and is orientable, then sigma hat is nothing but the disjoint union of two copies of sigma with the two possible orientations. Or another example is if sigma is a disk, then sigma hat is actually two sphere. So I take I take a disk, two copies of it, and I identify the boundary circle, so I get something which topologically is a two sphere, not geometrically, but one can deal with that. So that we do not need. And then until this ring manifold. Now, at the moment, without ribbon graph yet, I still use the same notation M sigma for it. I take this oriented double sigma hat times an interval, say -1, 1. And again, I divide out some equivalence relation, which is as follows now. If I take here in sigma hat, an equivalence class consists of a point and an orientation. And in the interval, I take some number t between -1 and 1. And this I identify with what I get by taking the opposite orientation here -t. And if my original manifold sigma is orientable, then actually there's simple description. But this also works for that case. And I will give you various examples of that. And one thing you can notice here is the boundary of M sigma, by definition, by construction, is sigma hat, and also there's a natural embedding of sigma into M sigma as a deformation retract. And correspondingly, there's a projection of M sigma to sigma. And this in particular means that there is no, in M sigma from this construction, there is no additional homological information than what is already contained in sigma that you can convince yourself about. I should mention that this is not all what one needs. technically, one for the surfaces that are used in the construction, they have to have the structure of what is called an extended surface. One has to choose Lagrangian subspace in the first real homology of a sigma hat, but I will suppress that. This can be done. So this is the three manifold M, and now the written graph. And this will take longer, but I hope I can cover various aspects of it. The basic idea is that the written graph and the three manifold amounts to what I call a geometric separation of left and right movers. Which are the constituents of a bulk field, say. And so I will first look at what happens if I take a bulk field. The bulk field was of the type phi, lambda, lambda prime, alpha. I want to construct a ribbon. I say the coupon is labeled by alpha, and there are two incoming ribbons, which I draw as lines, otherwise I will never be finished, which I label by lambda and lambda prime. So according to the rules of the topological field theory, locally, if I project this, alpha would just be a morphism in C from lambda or y lambda and y lambda prime to the invisible ribbon, which is the tensor. And now I say this is not not only have my worldsheet in which this is located, but I have my sigma hat and its three manifold. So I somewhere have the boundary of MS locally consists of two sheets, and then I say that I continue this one line to insertion on one sheet and the other line on the other sheet. And you have to be careful with orientations, and I might not do this all the time. So I now have a problem here. This space, as it is either zero-dimensional, namely if lambda prime is different from the from what I call lambda bar, so the label corresponding to the dual objects. And in general conformal field theories, and you have examples where you have other bulk fields. And this now you include by having an additional prescription, and that's where the Frobenius algebra A comes in. I say, so this we should think of being inside sigma, which is embedded in M sigma. And inside sigma, I take a line or ribbon labeled by A coming in and out. And in order that things can be consistent, I say that actually I take a dual triangulation of sigma where the edges are all labeled by the Frobenius algebra A, and the coupons or morphisms here are relevant morphisms for A. So what does this mean concretely? It depends on orientations. Assume we have this situation, two A lines coming in and one going out, and then we just have the product mu. A is a Frobenius algebra, so it's an algebra and a co-algebra. Co-algebra will be relevant if we have this situation. But we could also have a situation with three lines coming in. Then actually we will interpret this as follows. One going out here is coming in, and here we take the product and the co-unit. And there are many choices involved here, and one has to make sure that they do not play a role. And this is precisely the dots that I had in when I said some type of Frobenius algebra. Because it's Frobenius, we can change a situation of this type to a situation like that, by associativity or co-associativity or Frobenius, depending on orientations. I also require that I have this identity. This is what we call special, essentially, together with with a suitable normalization. This will be the dimension of A. A co-unit after unit should not be 0. And also, we will have situations corresponding. I suppress the pivotal structure. Where we have morphisms between A and A dual, either of this type, of this type. These are actually isomorphisms, and they should be equal with inserting the pivotal structure appropriately. And if I have all these properties, that's what I call a simple, a special symmetric Frobenius algebra, then it turns out that the particular choice of dual triangulation here does not play a role if I evaluate the resulting graph as a morphism in C.
So this graph is in sigma. That is, this graph is in sigma.
This graph, this part of the graph is in sigma, but then out of the graph, out of the, say, horizontal.
Sigma cross 0. Okay. Or
essentially, well,
space.
It's essentially sigma cross 0, but if there's a boundary, it's a bit more complicated.
Okay.
But then I have to go out of that whenever I have insertion of fields. And then I really have to describe this in terms of ribbons. So this will be flat, horizontal here, and you have to say something about how do you do this precisely, but you can do that. And you can ask, where does this come from? And it comes from realizing that if you that vector spaces are particularly simple modular fusion category. If I restrict to that case, then actually instead of a two-dimensional conformal field theory, I will deal with a two-dimensional topological field theory. And it is known that there is a classification of two-dimensional topological field theories oriented in terms of Frobenius algebras in vector spaces. And then it's natural to draw now Frobenius algebras in the more general category C. And then you see you need these additional properties in order to have triangulation independence here. And also you see, and this is now the next point, now our alpha here will be an element in the morphism space in C of now y lambda tensor A tensor y lambda prime to A. And in addition now, I want to have independence of the triangulation, not only if it's just there, but also if there are bulk field insertions. So I could look at a situation that I have an A line here, but I change the triangulation such that it comes here. And now it's important this lies in the middle. So this is above, so I go like that. And I realize that I have chosen the opposite convention in the picture I had before. Whereas if I have an A line here and I want to move it to here, then it will be, because it's on the bottom, it will go like that. And that means if I require that in both cases, both situations, I get the same, I actually deal with a bimodule morphisms where I have this particular bimodule structure on this object. And This gives me the description of the possible bulk fills that I have given you before, and I have given you that because this is what one knows from many models. So when this construction predicts statement about the space of bulk fills, which reproduces what is known in all those models. Now, maybe I give an example first before I continue to the case of defects. But please, if I try to erase anything here, stop me. Otherwise, I have to draw it again. So, I now look at the situation which is particularly simple, namely no field insertions at all. But it is it's a very special case, but also a very important one. This is what is called a torus partition function. This is when there are no field insertions, do not say correlator, but partition function. It's actually related to the fact that in some cases you can relate this to partitions. In particular, there will be certain coefficients which have to be integers. So in this case, sigma is a torus. Sigma hat, it case because it's closed and orientable. It's got two copies of it, and M sigma is just sigma hat cross minus 1, 1. Sigma cross minus 1, 1. So we have sigma hat cross minus 1, 1 divided by some equivalence relation in the oriented boundary-free situation. Just an answer replacing sigma hat there by sigma. So let's draw this. I do not have a three-dimensional blackboard here, so I indicate this as follows. So this is 1 minus 1s. The other one is obtained by identifying bottom, top and bottom, and then I have my interval minus 1. 1 here. Now I have to choose a dual triangulation. Because of the properties of A, it doesn't matter which one. I take the simplest one. This amounts to the following. One way to describe it is as follows. So as this is to be identified with what I have here, and then I take the co-product and the product of A to get this graph, and you can think of this as by looking at the description of the torus as square with identified segments of the boundary just by drawing two curves for the two non-contractible cycles that you have on it, and splitting up the four the vertex with 4 entries into a product in 2 with 3, which you interpret as a product and co-product. Now, and then this is the picture that I get for my 3 manifold, and then I apply reciprocal intervariance to this, apply to the number 1 in the complex numbers, and this is my correlator for the torus. Now we can ask, what does this mean and it just means what it says. We think of the correlator here as an element in a space of conformal blocks, and the space of conformal blocks is the one associated to the boundary of M sigma, so associated to the to two copies of the torus with opposite orientation. But for that space, there is a distinguished basis which are called characters. And it's the same in a sense as the characters of vertex operator algebra representations, provided we take this identification between a complex and topological modular functor, and then it becomes just the following. We take a full torus, and in the full torus we have, so again identified here, we have single flat ribbon length by lambda. And now I can say that this is often denoted by Z. I write Z as, I express Z as a linear combination in the spaces for, say, the inner boundary and the corresponding one for the outer boundary, taking into account the opposite orientation. So sigma Z will be written as a sum over lambda and mu, lambda, certain complex numbers in general. And then this, for simplicity, I just call them chi lambda. So this would be chi lambda. And so chi lambda, chi mu, let's call it bar for the opposite orientation. And then these numbers here are what people in many applications are interested in. And now one can show by using the following observation. If I denote this morphism from A to A by P, and this is in fact an idempotent. And it would be nice. I have a kind of movie, but just consisting of some individual pictures where you take two copies, compose them, and then see how we use the properties of A to simplify this picture and go back to B. Because of this, sand, if you look at this picture, is the trace of this morphism, which is simply close. So it's a trace of an idempotent, and therefore it follows that Z lambda mu is in fact a non-negative integer. So that you prove very easily, and this is one requirement that this partition function should fulfill. Also, you want to have it mapping class group invariant. The relevant mapping class group here is the one of the torus. So for this we had these generators S and T, and you can show if I take S and T really as given by what I obtain by modular transformations of the real characters of the set regarded as a matrix in these labels commutes with S and T. And actually, this is very easy to see because in any modular transformation of the torus in terms of a chosen dual triangulation just means that I choose a different triangulation. But I know all triangulations will give the same results. So this will this becomes immediate.
What is A?
A
is a special Frobenius algebra.
A is special symmetric Frobenius algebra. And I will also, this doesn't play a role yet, but for some other aspects, I will assume require it to be simple. I still have a minute. So this example is in the absence of bulk fills. You can also look at situations where there are bulk fills, but for drawing things, it becomes a bit lengthy, so I will not give you any such example. Instead, I'll continue to including boundaries and boundary fields, and then I will give you an example with that situation. So that would be the next thing to do, but actually it turns out it's better to first generalize this to the situation that I will allow for defect lines. So some label B, we already know these are bimodules now. I have A and A prime on the different sides, and this corresponds to the situation now that somewhere in my worksheet I should have to use a different. That's definitely yellow for it. Like here, so somewhere now in my worksheet I have such a defect, but nobody forbids me to take. I forgot to say this defect should be what one calls for topological defects. If I change locally the position a little bit without touching other defect lines and without touching field insertions, the correlator should not change. So I can do that, and therefore, in particular, I can look at the situation that on my triangulation here, I have that in this part of the triangulation, I actually have defect lines, possibly labeled by two different defect conditions, B and B prime. But I already told you B and B prime would be A prime bimodules. Now, in this situation, on one side, I would have A, and on the other side, would have A prime. Of course, globally, this must fit together. So these lines have to be closed or end on the boundary. So then the alpha here will be a morphism, an A prime bimodule morphism, where instead of A and A here, I have B and B prime. And these are precisely the defect fields, the spaces of defect fields that I have told you about. So this simply is a slight, if you wish, generalization of the situation with bulk fills, but it also tells you now, or explains to some extent, why I should look at bimodules, because I have this dual triangulation. Part of it is now my B and B prime lines, but on one side, there will be part of the dual triangulation where all the lines are labeled by A prime, and on the other side, all are labeled by A. And when they come together for the here, I have to give a morphism here, and a natural morphism, which in such a way that it's compatible with choice of with change of the choice of dual triangulation, is that it's an action of A prime from the right and here of A from the left, and they should be compatible. Okay, and I am over time. I should stop. Yeah. Let me give an example. With defect line, I looked at a torus with two parallel and non-contractible defect lines. So what I then get by my prescription is again torus times the interval, which I also can think of as a full torus here with a small full torus cut out. And my picture will now be as follows. From the defect line, let's call them B and B prime. I have these lines here, and let's just in order that I can use precisely the picture that I have in my notes, assume orientation in this side. Now, one of them will be an A prime bimodule, and the other necessarily then an A prime A bimodule. And I will, let's assume we have the situation that here I have an A prime. Then so here I have an action of A prime, and here also, and I can bring them together in this way. And analogously for A, I have an action here and an action there. Now I'm getting the double, and I continue this again. This goes behind this inner cut out full torus like that. So we get a picture roughly looking like the one here, where this is labeled by A. And now just like this particular morphism I have shown, and for P is an idempotent, you can also show that the morphism that results from here is an idempotent. So if I now expand this again in the basis of characters for the inner and outer boundary torus, that amounts, so this will give me some set with labels B prime. Okay? And if I now look at the expansion of this with respect to characters in the same way as I did for the torus partition function, this amounts to have some line labeled say by lambda in the interior here, and then there is no nothing, no boundary left here, because I have glued in a full cylinder, and the other as the lambda prime is here. And also I have, so this is on the outside, I have glued full torus from the outside. Altogether, what I will get is a three-manifold topologically S2. Horizontally, I will have an S2, so I start with a circuit from the interval. I insert something here and something outside. I will get an S2. This is S2 cross S1. I can calculate these corresponding invariants again. And again, this will be the trace of this idempotent. So in particular, I will get that this is again a non-negative integer. I will also get that in the special case that I just take the trivial bimodules. I just get back the torus partition function, not surprisingly. And several other properties. Let me just mention one, which is nice. I now think of these numbers as matrices in the labels B and B prime. They will have some extra labels lambda and lambda prime, and then one gets z lambda prime multiplied as matrices in these, which z mu prime is equal to sum over nu, and then n lambda nu and sum over nu prime and lambda prime nu prime and then z nu prime. This is called, what one says that these furnish a representation of the double fusion algebra, because the lambda use is dimensions of spaces of 3-point couplings. Remember, where are the structure constants of the complexified Grothendieck ring. But now, that was about having defects. Now we assume that we allow for boundaries, and the reason why I first click a defect is I can think of a boundary, just a defect. Let's look at the situation where I have the same A on both sides. No defect line here at all. So I have I will here some dual triangulation. You can end on the boundary labeled by A, and I can think of, on the other side there's nothing. These are end of the world boundaries, but I can think of having here the trivial Frobenius algebra 1, and then M will be an A, an A1 Y module, but this is the same as an A module. And then a natural prescription is that if I have such a junction here, so this will be a morphism from the object A tensor M. If I think of M as an, well, maybe I should write M dot. But this is the object underlying an A module to M dot. But not every morphism should appear here, not every arbitrary. It's just like for these morphisms here, I take the structural morphisms, product, co-product, and so on. It's natural to take the morphism row here. So M is an object and dot together with a morphism of this type. And that's the one I prescribe. And now if we have a boundary field, let's see, did I mention? I might not have. Then I will have the situation that I have my psi here, so on two sides of it, I will have boundary condition M, respectively M prime. And then it turns out that there is an additional label, like that, lambda, which again is a line which I connect to the boundary of the three manifold, which is sigma hat. And let me show this to you by in the special case of sigma being the disk. But first notice that then the space of morphisms here will be in the first place morphisms from M tensor lambda to M prime. But again, not all of them should be relevant. I require that I look at this as an A module and allow only for A module morphisms, and this gives the description of boundary fields that I already mentioned. Now, what about this line here in this specific situation? So we have, if we have the disk, sigma hat is the two sphere, and M sigma or MS is the three ball. How can we think of this? When we have our disk here. On each point in the disk in our construction, we choose 2 points on the on sigma hat, except if it's a boundary point. And then the three manifold we can think of to each point here attaching an interval from -1 to 1. We do this everywhere in the interior. If we are on a boundary point, we have this non-trivial identification, which essentially amounts to taking the interval and identifying points like that. And accordingly, I will have my tools here, and then intervals of this type, half intervals. And then these lambda lines will have to follow these half intervals analogously, and this I will consider afterwards. If we have a point in the interior, these yellow lines and the 2 points on the boundary of MS, I can think of going along these intervals. And that's the next thing I will look at. So we look at the example of this type, but without a boundary field, but rather just with one bound field. So we will have a bound field here. Let's call it for the moment phi lambda prime alpha. So we have a lambda line ending, say, here, and a lambda prime line ending on the other side. And then we need our dual triangulation. One way to choose it is just like that. If I would add something more here, I can use. Here I have representation morphisms. I can use the representation properties to replace this by such a triangulation, and then I can use the special property to remove this. So on. So this is the simplest triangulation I'm looking at. So here I have row, and here I have also row. Depending on orientations, one has to be careful. I have a boundary condition here. I should have drawn this in green. M. And then if I'm careful with orientations, A should be incoming here and here, but I want to have A incoming also here, then I would add such a unit together with the co-product. That's just a binding. And now this is then the three manifold with embedded ribbon graph that I associate to this situation. In this case, there is still a preferred basis for the space of blocks on the sphere with two insertions, lambda and lambda prime. But actually, this is non-zero only if, depending on orientations here in my choice of orientations, we actually need, in this case, that lambda prime is the dual of lambda. And then I have a basis of the base of blocks on S2 with insertions lambda and lambda prime, just given by the three ball with single line lambda, label lambda n. And then I do the analogous thing as I did when expanding the torus partition function Z in terms of that basis of characters, which gave me coefficient Z lambda mu. Now I get coefficients here. But here I have my 2-ball, a 3-ball. I glue another 3-ball from the outside. By this, I get a 3-sphere. And in that 3-sphere, so if I glue this here, what I get is S3 with a ribbon graph inside, which looks like following. I changed orientations here to make it look simpler. So here I have M, here I have lambda, and then I have my Ala in between. And then I have A, where here I have a morphism of this type. I have described for actually one can no, I've done it like that. So I get a written graph like this in S3. Remember, S3 has no boundary. Therefore, if I now apply residual interarea to this graph, I will get a number up to some normalization, and this is the number which corresponds to this the morphism described by this string diagram for the category C. Yeah, so all the beautiful morphisms are in C, but I have to remember that this is with an A module. So at these points here, I have the action of A on N. And so these are coefficients. C is a depending on lambda and M. They are what they are. Actually, one can show various properties of those, and in the physics literature, these coefficients have been introduced many years before these pictures were drawn. So, by some heuristic arguments, one could derive some properties of those, and all of those properties actually can be derived from this description as a written graph. Special case, A being the trivial for Venus algebra, then the labels for A modules are the same as those for objects in C. And you see what I get here is just the graph of the hop link, which corresponds to the model S matrix. So these numbers here are generalizations of the modular S matrix, and in fact one can relate them by using some additional rewriting here to the modular S transformation matrix, not of a character. So for what I get for in the case of torus partition function, but for the situation that I have a torus with one insertion of A. And there is another example, which I think I now can take away this. I want to show this is another partition function, but no fields involved. And this is what one calls the annulus or cylinder partition function. With some boundary conditions, M and N prime probably. So in this case, sigma is an annulus or cylinder, so let's write it as S1 times an interval. Then sigma hat is well, I have to no, sorry, sigma hat is just let's take this as an annulus. It has two boundary circles. I take two copies of it and glue it along the boundary. So what I get is a torus. And sigma ms is then again a disk. Well, it's then a disk times S1, so it looks like the color. So here I have my disk, and the S1 is again identifying bottom and top. And what I will get in this case is very similar to, you can think of it even as a special case of what we have seen for the torus partition function, for the torus with two defect line insertions. So now I have two lines, draw them again in yellow, which are these boundary conditions. But then I have only one of these. Here I have row M for M prime, and here I have A. Again, the boundary of this is a torus, so I can expand it in the natural basis of characters. So this would be the annulus. With M and N prime. This would be RT applied to this, and then applied to 1 in the complex numbers, and then I can write this as a sum over coefficients M prime and say lambda, where I have my chi lambdas here. And then again, the morphism that we see here is a special case of what I claim for the defects is idempotent. So we get a trace of an idempotent, and then in particular on those, this implies that these are non-negative integers. Well, in this case, maybe I show how you that this is idempotent. And I change orientation a bit, and it's easier or quicker to draw. Let's look at this situation. So this is the relevant morphism here. Now I take this twice. Here I have representation morphisms. Using the representation property, I can rewrite this as having a single row on both sides, and then graph like this. And then using Frobenius, so this here I'm using Frobenius, this can be redrawn as this graph, and then using special, this goes away and go back to what I have just missing. And so we have to these are again integers, you have some other properties which I will not write down. Just one, namely the analysis coefficients give you a representation of the fusion rules. Historically, this has been called the NIM rep, NIM for non-negative integer matrix. So analysis lambda. So I take this as a matrix now in these M prime labels, and lambda prime here is some on the row and lambda prime. That's all I wanted to present for the situation where I start with an oriented worksheet. I will say a few things about the non-oriented case afterwards, but let me just mention that we have a prescription which I can use to give a ribbon graph in a zero+3 manifold for any arbitrary correlator for an oriented worksheet. Of course, we have not looked at all of them. There are infinitely many. So when I now claim that this gives a consistent system of correlators, you might think that this could be very hard to show. There are infinitely many correlators and infinitely many consistency conditions. But the important thing is all these consistency conditions are local. Namely, well, we have consistency conditions which are not, namely the model or mapping class group invariance. But the mapping class group invariance is very easy to see. It just amounts to independence of the choice of dual triangulation. And this is just all these properties we require from our algebra A. But the compatibility with sewing is actually very complicated. But importantly, if you gluing or sewing is a local operation. What happens in the rest of the of your manifolds is unimportant, and therefore you can if you have a under control, what happens locally, you just apply this at all places where you want to sew. And is it still complicated? I would not be able to present a complete proof in one lecture, I think. And also, it's purely constructive. So we describe the situation in sufficient detail, and then look at well, and then do certain manipulations. And conceptually, there is not much to say. One simply shows that one has this compatibility, but one doesn't really learn anything new from it. Okay, now briefly, I don't have to do much about this, but briefly about the situation with non-oriented or non-oriented at least. Worksheets and therefore corresponding sigmas. One can do this in an interesting way, in particular concerning some issues in string theory already for the analyst by just not considering as oriented. But I will not treat that. Only two examples of worksheet which is actually not orientable in the first place. But let me first point out here that we need additional structure on the algebra A. The prescription for getting this double cover sigma orange cover silver hat and the three manifold is as before, except that if sigma is not orientable, it's much harder to draw the resulting three manifolds. I will try in one case to say something about it. But now for A, we actually, it should still be a symmetric special Frobenius algebra. About requiring also simple, I will say something later. But we also need what is called a inversion. And let's call it sigma. And then A together with reversion is called a Young algebra, and I will not tell you that name comes from. What is a reversion? A reversion is a morphism from A to A. That's denoted like that. Such that, first of all, it's an algebra morphism from A to the opposite algebra, so it's compatible with the unit, and it's compatible with the product, but up to a grading, the self-grading of A. And in addition, it squares to the twist of A. This is, or you should think of this as a generalization of an algebra, of an ordinary K algebra with involution. If your category is symmetric, then the twists will be identities, and this all this has the square of sigma as the identity. And one important aspect of this is the following. If I have an A module M, so more letters, at some point, page ones. If I have a left module M, then if I take the dual of M and a simple morphism here, this will be a right module, and this is easy to describe. Namely, this is M dual. I already know an action on M, so I use the snake identity to have a piece where I have M here. On M, I can add with A from the left, and you easily convince yourself that this gives you an action. So this would be rho tilde, an action of A from the right.
So this is not an involution. The square is theta.
It's not an involution. I said it's an analog. So therefore, we have a different name for it.
Okay.
And when the name comes from something else.
Yeah.
Here I have not used it. That you always have for an alpha.
No, this is fine. I'm still
now if we have A sigma, then there is also on M dual a row hand left module structure. And that is again easy to draw. I have the left module and left action of A. How can I get A now to the left? I have to somehow get this through. And one way to do it is as follows. Here I have the pivot structure, and then I have my sigma. And you can check that this is that gives you a depth modulo. And up to essentially a twist, this is the same as if you just would break through and then. And maybe I should just mention here that whenever I have an algebra A and an algebra A prime, then on the tensor product as objects, I have a natural algebra structure, maybe looking like this. Here we have A and A prime, and here A prime, just using the braiding, well, maybe braiding here. Using the opposite braiding, one gets the co-algebra structure such that these fit together with to be again a natural structure for Venus algebra tensor product. It's no longer true that if I take two commutative algebras, that the tensor product is again commutative because of this braiding here. But important for us now is that this A and A prime are Yandel algebras. Then it's not true that A tensor A prime together with sigma tensor sigma prime is a Yandel algebra. But that does not work. So certain things become more complicated. Let me just give you one example, and this is the Klein bottle. Take sigma equal to the Klein bottle. Sigma hat, in this case, is a torus. So it's similar as with the annulus, but now M sigma or MS, I should write, it can be described as follows. I take this product here and identify 0 x t numbers x and t in these with 1 x. I should call this y maybe, and x 0 and t with 1 minus x 0, and this should be and minus 3. Just amounts to, in the end, obtaining. Because this is a torus, there is again the space of again the characters as natural basis for the blocks. So for this Klein bottle amplitude, will get something which I just call K, which is a sum over lambda coefficients K lambda times phi lambda. And that's for this chi lambda, I get up to applying with Tikin-Torayev the following picture. It looks a bit similar to what I had for the torus partition function. So let me just start with that. So I have get something like this. I have A here, but then I need my sigma here, and then we will see why. Namely, the identification here is. Why don't I have it here? No, I have it. It's if I take on this disk here, as a unit disk, I take in coordinates r phi. I get the identification that on the top, this is identified with the bottom, but with 1 over r and minus. So, and this changes the orientation. And accordingly, actually, I should not draw this like that, but there will be a half twist of my ribbon. So if my ribbon, if I draw this as ribbons, so say the black side here, it will show the white side here. I should indicate this half twist directly, and then by this identification, when I do that, it's twisted back so that it becomes here. So this is what I would get without expanding. If I expand in the case of the torus, I inserted 2 lines labeled lambda and mu. In principle, I do this also here, but now if I have lambda here, the other line, because of the identification, will not, what gets out here will come in here with a half twist, again labeled by lambda. So therefore, there's only a single label here. And now evaluating this is considerably more complicated than the other cases. And actually, I do not remember any details about it, but one can show, in particular, k lambda is an integer, not necessarily non-negative. It's such that I get the same integer if I replace lambda by lambda bar. Not so surprising, because somehow replacing lambda and lambda bar you can undo by looking at this from behind. And then importantly, and this has an interpretation in string theory, if I look at the diagonal coefficient z lambda lambda of the torus partition function and add to this line bottle k lambda, then this is in fact a non-negative integer, and it's between 0 and z lambda lambda. So k can be smaller than k lambda can be smaller than 0, but in absolute value they're not more than z lambda lambda, and also the difference between the two is an even integer, or the sum is an even integer. Now I have maybe 2 minutes left. So let me just say a few things in words. So first of all, the main result is this bijection that in this way I get, with all these prescriptions, in the orientable case, I get a consistent system of correlators, and the systems I get are in bijection with Morita classes of these algebras. And in order to have really a bijection, one now has the additional requirement, first of all, that A is simple, meaning it's simple as a bimodule over itself. And for the quantum field theory interpretation of that is you have a unique vacuum, whatever that means. And in addition, you have to require that your theory is non-degenerate, in the sense that the system of 2-point functions on the sphere has some non-degeneracy, and the 2 bulk fields on the sphere, and the same for 2 boundary fields on the disk. And then this is completely proven. What is also proven is not the bijection, but the fact that you get a consistent system when you the statement is when I just talk about one Morita class of algebras, it's without defects in general, or maybe with AA defects. But if I allow for general defects, then I have to apply this statement in each two stratum labeled by one of those algebras separately. And one can show that factorization still works nicely in the presence of arbitrary defects. One can also show that it works in the non-orientable case, but I don't think that it has been formally proven that there's a bijection too. And now one has to be careful. If I have two algebras which are Morita equivalent, and I have a Jandl structure reversion on one of them, I don't necessarily have one on the other. So there's a refinement of Morita equivalence. And then the statement will be that such refined classes will be in one-to-one correspondence. But that, as I said, has not been formally proven. Then there are various additional specific results that you can derive. So, for example, if your algebra is of the type that each simple subobject is an invertible object, then there is a relation to group cohomology, and by the way, a relation to quadratic forms. And the point is that maybe that's the end of the lecture. I'm just mentioning if you restrict, maybe I said it already, if you restrict the associator of C, or what is left in the strictified situation from the associator of C, that is to the Picard subcategory, then you get a three-co cycle on that. If you restrict the braiding to the Picard subcategory, you get a two-co chain, but this three-co cycle and two-co chain fit together into what is called an abelian three-co cycle. And the two-co chain that appears there is very closely related to quadratic form. And in fact, well, it's essentially the same depending on some conventions. And that quadratic form, on the other hand, can also be described as follows. You have an invertible object, X. So X tensor X load is isomorphic to 1. Then it turns out X tensor Y lambda is some other Y lambda prime. And now this will actually correspond to some element in the Picard group. So let's call this LG. And then lambda prime, we can think of acting with G on lambda. And then the quadratic form is given by the twist eigenvalue of G applied to lambda divided by T plus G. And maybe I should stop here. Okay, I'll take a photo.